Why do we need to call 0_grad in PyTorch? Why does 0_grad need to be called during training?
In PyTorch, for every mini-batch during the training phase, we typically want to explicitly set the gradients to 0 before starting to do backpropagation, i.e., updating the weights and biases, because PyTorch accumulates the gradients on subsequent backward passes. This accumulating behavior is convenient while training RNNs or when we want to compute the gradient of the loss summed over multiple mini-batches. So, the default action has been set to accumulate, i.e. sum, the gradients on every loss.backward call. Because of this, when you start your training loop, ideally you should zero out the gradients so that you do the parameter update correctly. Otherwise, the gradient would be a combination of the old gradient, which you have already used to update your model parameters, and the newly computed gradient. It would therefore point in some other direction than the intended direction towards the minimum, or maximum, in case of maximization objectives. Here is a simple example. Alternatively, if you're doing a vanilla gradient descent, then note: the accumulation, i.e., sum, of gradients happens when .backward is called on the loss tensor. As of v1.7.0, PyTorch offers the option to reset the gradients to none, optimizer.0_grad set _to _none equals true, instead of filling them with a tensor of zeros. The docs claim that this setting reduces memory requirements and slightly improves performance, but might be error-prone if not handled carefully.
Although the idea can be derived from the chosen answer, I feel like I want to write that explicitly. Being able to decide when to call optimizer.0_grad and optimizer.step provides more freedom on how gradients are accumulated and applied by the optimizer in the training loop. This is crucial when the model or input data is big and one training batch do not fit on the CU. Here in this example, there are two arguments, named train_batch_size and gradient_accumulation_steps. Train_batch_size is the batch size for the forward pass, following the loss.backward. This is limited by the CU memory. Gradient_accumulation_steps is the actual training batch size, where loss from multiple forward pass is accumulated. This is not limited by the CU memory. From this example, you can see how optimizer.0_grad may followed by optimizer.step but not loss.backward. Loss.backward is invoked in every single iteration, line 216, but optimizer.0_grad and optimizer.step is only invoked when the number of accumulated train batch equals the gradient_accumulation_steps, line 227 inside the if block in line 219. Also, someone is asking about the equivalent method in TensorFlow. I guess tf.gradientTape serves the same purpose.
Why gradients? The gradient suggests to the optimizer what direction to step in. Every time you process a batch of inputs with .backward, you accumulate suggestions of where to step. Notice that a suggestion is much weaker than a decision. When you call optimizer.step, the optimizer uses these suggestions to make actual decisions of where to actually step. These decisions may be influenced by the learning rate, past steps, for example momentum, and past weights, for example SWA. The optimizer reads the suggestions and then steps in a direction that it hopes will minimize future losses. Why zero the gradients? Once you've completed a step, you don't really need to keep track of your previous suggestion, i.e. gradients, of where to step. By zeroing the gradients, you are throwing away this information. Some optimizers already keep track of this information automatically and internally. With the next batch of inputs, you begin from a clean slate to suggest where to step next. This suggestion is pure and not influenced by the past. You then feed this pure information to the optimizer, which then decides exactly where to step. Of course, you can decide to hold on to previous gradients, but that information is somewhat outdated since you're in an entirely new spot on the lost surface. Who is to say that the best direction to go next is still the same as the previous? It might be completely different. That's why most popular optimization algorithms throw most of that outdated information away, by zeroing the gradients. Another alternative, deleting gradients completely, instead of zeroing. Instead of zeroing the gradients, you can also delete them entirely. The PyTorch Performance Tuning Guide suggests. But one of the developers mentions this in a comment from 5 years ago. The main difference is that the tensor containing the gradients will not be reallocated at every backward pass. Since memory allocation is quite expensive, especially on Q, this is much more efficient. There are other subtle differences between the two, like some optimizers that behave differently if a gradient is 0 or none. I'm sure there are other places that behave like that. On the other hand, in-place operations are usually not considered necessary or even suboptimal in some cases, so I guess you WRT the performance of either method.
In simple terms, we need 0_grad. Because when we start a training loop, we do not want past gradients or past results to interfere with our current results. BQ's how PyTorch works, as it collects/accumulates the gradients on backpropagation, and if the past results may mix up and give us the wrong results, so we set the gradient to 0 every time we go through the loop. Here is an example. In this for loop, if we do not set the optimizer to 0 every time the past value, it may get it up and changes the result. So we use 0_grad to not face the wrong accumulated results.
$0_grad restarts looping without losses from the last step if you use the gradient method for decreasing the error, or losses. If you do not use $0_grad, the loss will increase not decrease as required. For example, if you use $0_grad, you will get the following output. If you do not use $0_grad, you will get the following output.